Welcome to Rust Belt Science. I'm your host, Maggie Fink.
And I'm Shahir Risk.
And today we have with us Dr. Roman Gerasimov, who is a postdoctoral researcher here at the University of Notre Dame in astrophysics. So I'm very excited to have you here. I've heard great things. This is our first time meeting, and we have a lot of cool questions we want to ask about outer space and all the cool things you research. So welcome.
Yeah, I'm really happy to be here. I'm excited.
Cool. So the first thing we actually like to ask our guests is not a science question, because we want to introduce scientists as kind of normal people who do normal things as well. We don't just do research. Are you listening to, reading, or watching anything interesting, fun right now in your life? And if no, that's fine too. But
well, we had the Oscars last weekend.
Oh, yes.
So
yes.
I've been desperately trying to catch up on all of the nominees.
Okay.
So a bit of a tradition that I do every year.
Okay.
Nothing to do with science.
Yeah. Well, do you have any opinions on the winners or anything that you think was incorrect?
I was rooting for The Brutalist. I really liked it. I'm not too opposed to the winner that they ended up choosing. It would not have been my choice.
Sure.
But
Yeah.
I'm okay with it.
Okay.
I accepted it.
All right. Well, didn't Adrian Brody won Best Actor?
He did, yeah.
So, okay. So it got some acclaim. I don't think I've seen anything that was nominated. I usually have seen at least one or two. You don't really follow the Oscars, do you, Shahir?
I did not follow it this year.
Yeah.
I usually try to. I'm kind of late to the game.
Yeah, that's all right.
But I will watch the movies.
Yeah.
I will watch the
Okay.
movies. The Brutalist has been recommended, so it's just a matter of finding the time to do it. I'm really interested.
Yeah, you are going to need a lot of time for The Brutalist in particular.
Yeah, that's kind of inherent in the name, it sounds
Yeah.
like. It's going to be... Well, the Oscars are the first. Like, most people answer that question, and a lot of the researchers are reading science fiction or something, which I don't really do. But this is like the first one. I'm like, oh, yeah, I can follow...
Popular culture.
Yeah, I love pop culture and movies and everything. So, cool. Yeah, by the time this airs, I don't know how far away the Oscars would...
We're talking about the 2025 Oscars.
Correct,
Yes.
correct.
Hopefully before the next.
I'm sure that will be the case. But cool. Well, thanks for that. And if anybody wants to go rewatch anything from the Oscars, go do it and all the movies were great. Okay, so easy. You passed the first question.
First question.
Flying colors.
Yeah, 5 stars. Well, I want to talk a little bit about the research that you're doing and your research interests in general. And you're interested in very old stars. These are the ones that formed at the very beginning of the universe, right? And just to tell our lovely listeners, how old is the universe? Just so that we can have a starting point here. How old is our universe? And how do we know the age of the different stars?
Yeah, those are very good questions. So we believe that the universe is approximately 13.8 billion years old.
That's billion with a B.
That's billion with a B.
Wow.
Okay, all right. So that's 1,000 million years. Each billion is 1,000 million years.
That's correct.
Okay, all right.
I actually think it's most useful to think about like lifetimes on the scale of billions of years in terms of the lifetime of the sun, which for comparison is about 4.5 billion years. So that's sort of our local place in the universe. And so the universe is older, but not by a lot, something like a factor of 3.
Yeah. So the universe is only about 3 times older than our sun that we look at and see every day.
Yeah, that's about right.
Wow. Okay.
That's crazy. It's hard to fathom a number that big. It's like there's no kind of frame of reference for anything that's incomprehensible. Might as well be eternal in my mind, I feel like. I think that's partially why I'm a little afraid of outer space, because it is just like this old, vast thing we know so very little about.
But I think, as you're a microbiologist.
Correct, I'm a microbiologist.
Biochemist, microbiologist, and you study very, very, very small things.
Sure.
And sometimes we have to count those very small things in very large numbers.
Yeah.
And to some people, that could be unfathomably small. So I think it's just a different end of the spectrum. Roman, what do you think?
Well, since we're talking about microbiology, I suppose like the time scale at which the universe evolves is not that different to the time scale of biological evolution also. So that's another, I suppose, useful way to think about it.
Yeah,
That's
life
true.
is 2.5, 3 billion, maybe a little bit older.
Yep, something like
Yeah,
that.
with a B still.
Wow.
Yeah.
Yeah, I guess
they're
that's
bacteria.
true. Yeah, and it is interesting. We operate our research as just complete opposite ends of the size scale in so many ways.
Yeah.
Which, I find things that are microscopic and nanoscopic kind of comforting in a way.
Yeah.
Do you find the vastness of the universe kind of a comforting idea? Maybe that's a stupid question, I don't know, but I would feel lost thinking about such vastness all day.
Well, what is interesting is that all of the size scales are almost equally relevant in a sense. So on one hand, the universe is very large. Then on the other hand, we primarily study the universe through the light that we see in the sky by pointing our telescopes at it. And that light is produced at the microscopic level. So we have to understand the universe on the scale of atoms also in order to be able to do astronomy. So they're not as disconnected, those small scales and large scales, as most people think.
That's an interesting perspective. Yeah, that helps. Every time I talk to somebody who studies outer space things, I feel a little bit more comforted. I'm like, oh, there is something kind of tangible there that can be studied and researched.
Good. We're putting you on the next mission to Mars.
No thanks.
Well, so that answers the first question. How old is our universe? It's fairly old, but also not that old. And how do we know the age of the different stars that are not all the same age? So how do we know the age of the stars that we're looking at?
Yeah, so I suppose there are two parts to this question. And I like to draw analogies with archaeology. So if you, say, find an relic of ancient Egypt, there are sort of two levels of precision that you can approach dating it. You might just be interested in figuring out what broad time period it belongs to, like whether it's the Old Kingdom or the New Kingdom. And that could be relatively easy to tell. I don't know anything about archaeology, but I would imagine that from the writing style and the style of art, you'd be able to tell that vaguely. Alternatively, you could go to full precision and ask, okay, what year or what century was this made? And that's going to be a much more difficult question to answer. So presumably you would have to use some kind of radioisotope dating, and you're not going to be able to do it for any artifact. You would only be able to do it in special cases. And astronomy works in a very similar way. So on a sort of superficial level, you can look at a star and you can determine if that star is old by certain broad features. You would not be able to date it precisely. So, for example, older stars tend to be less chemically complex. Chemical complexity has evolved over the course of the lifetime of the universe. So if you're looking at a star whose chemical composition is mostly hydrogen and helium, the two elements that were made in the Big Bang at the very beginning of time, and very little of everything else, then it looks like an old star. You may not be able to tell how old it is, but you can broadly place it in a certain time period in the history of the universe. You could also look at how that star moves. All of the younger stars tend to be a little bit more organized because our galaxy got more organized over time. But all of the older stars are moving in a more chaotic way, simply because when they first formed, the universe and our galaxy in particular was a bit less organized. But then you can also go to a deeper level of precision. You could try and actually estimate the age of the star in terms of billions of years. And that can be very difficult to do. In fact, I am working on developing a new method for doing it in certain special cases. But the most typical way of doing that, the most standard way, is you would have to look for a star that is actively dying. So if you're looking at a star that's in the middle of its lifetime, like the sun, estimating its age would be very difficult.
Right.
But if you're looking at a star that's actively dying, you know it's at the end of its lifespan. And so if you can work out what lifespan that star is supposed to have based on the type of that star, then you know that it formed that long ago.
I see.
So this, again, I might have a stupid question, but I'm not an astronomer or anything.
Yeah.
I've heard a lot about stars dying, and I kind of just pretend like I know exactly what that means. But now that we're talking about that, how does a star die? Like what, right? How does something that isn't a life die? And yeah, I can't really comprehend what that.
Yeah, what is the death of a star?
Yeah, and like, what are some of the signatures? How do you know that a star is dying? What does that look like? What do you measure from that to determine that, this is a dying star as opposed to one that's in the middle of its life?
Yeah, it's a very fair question. I suppose astronomers are guilty of not defining what they mean by life and death in this case. So very broadly, a star is a balance of two things happening at the same time. So like on one hand, there is gravity that is trying to squish that star into a point, so self-weight of that star. And then on the other hand, there's nuclear fusion, right? So if you look at the center of the star, then the temperatures and pressures there are so hot that actually turns hydrogen into helium. And that produces a lot of energy and a lot of heat, and that helps prevent that collapse. So when you're looking at a star like the sun, that is what astronomers would call a living star, a more technical term, a main sequence star. Those two processes are in perfect balance, and the star is maintaining roughly the same temperature, roughly the same radius over an extended period of time. But you can't be doing that forever, because at some point you're going to run out of that fuel in the center of the star that is powering your star. And so at some point, your star is going to fizzle out and gravity is going to take over. And that is what we mean by death in this case. And the way any individual star is going to die is going to depend on how massive that star is. So some of the bigger stars end their lives in huge explosions, supernova explosions. Some of the smaller stars are a little bit less dramatic. For example, the sun is going to turn into something that we call a red giant. It's going to get much redder and much bigger. And that is something that you can see.
Wow. When is that going to happen? Should I set my calendar?
Well, the lifespan of the sun is about 10 billion years, and it's about 5 billion years in. So.
Oh, man. So we were half.
All right.
Okay.
I think your calendar will be irrelevant by that point.
I think so, too.
But
Yeah.
sorry to inform you. No, that explanation actually really helps me kind of, visualize what's happening and understand why it's important to study those and things. I've never heard it really explained that way. That was super helpful, actually. And it's like, you kind of know these things like a star. There's energy and whatever, but what actually is happening in a star has not always been as clear to me. So I can imagine our listeners as well would appreciate that. And I think all scientists are guilty of kind of assuming people understand some things, and we talk about them as if, everyone just kind of knows the simple thing that we take for granted. So
yeah, it's true. We're all guilty of it.
Yeah, but that was an excellent explanation.
That was very good.
And now we can continue on with more.
But
in-depth
along those same lines, you talk about hydrogen coming together. So two hydrogens would come together, and they would fuse, and then eventually turn into helium, and that's a different element altogether. Now, I'm a biochemist. I'm a chemist, and really all we do is chemical reactions, where hydrogen will always be hydrogen. It might combine with different things. Hydrogen with chlorine, it'll be hydrochloric acid or whatever. Helium will always be helium. Sodium will always be sodium. But in these stars, you get the nuclear reactions happening. That means that elements can actually become different elements on the periodic table. And they can just change from one thing to another, which is fascinating. And in fact, this is, probably one of the things that you're studying, and this is this idea of galactic archaeology that you've talked about, is using the stars to actually understand how the elements themselves that we see on the periodic table, like oxygen and other things, actually formed in the first place. So tell us a little bit more about how do these things form, and how do we know that?
Yeah, that's exactly right. So if we look at the universe when it first formed, so if we go back 13.8 billion years to the Big Bang, because of an interesting coincidence in nuclear physics, so it turns out that only two elements of the periodic table could be produced by the Big Bang itself in appreciable quantities, and those are hydrogen and helium. So the universe started off with something like 75% hydrogen, 25% helium, and pretty much nothing else. Maybe trace amounts of lithium, the third element. But the quantity of all of the other elements would be completely negligible compared to hydrogen and helium. And then if we look at the universe today, it is still mostly hydrogen and helium.
Yes.
But approximately 2% of it is made of everything else in the periodic table. And 2% doesn't sound like much, but that's the stuff that everything that we know is made of. That's the stuff that I'm made of, that our planet is made of. So there's a very important 2%. In fact, astronomers like to call everything that's not hydrogen and helium just metals. And I know that, chemists hate that.
Of course. Yeah, we don't like
That's
that.
atrocious.
You're going to call carbon a metal?
Oh,
my
my
gosh.
goodness.
I'm going to have a heart attack.
Yeah, and we believe that all of those metals were produced in stars through various nuclear processes. Right, so unlike chemical reactions that are happening at much lower energies, where carbon will remain carbon, perhaps in some molecular compound, but a carbon nonetheless. Nuclear reactions are energetic enough that elements can become other elements.
Yes.
And so over the course of those 13.8 billion years, perhaps a little less than that because stars did not form right away, but inside stars, those nuclear reactions happened and they produced the rest of the periodic table.
Wow.
And so galactic archaeology has been mentioned.
Yes.
The idea of galactic archaeology is to use stars as fossilized record of that process.
Wow.
And so if I look at a star that is 10 billion years old, the chemical composition of that star would be representative of the chemical composition of the universe 10 billion years ago.
Okay.
So by looking at stars at various ages, you can almost reconstruct this movie that shows how all of the elements of the periodic table were produced.
Yeah. So then you see like a newer star and you say, oh, here comes oxygen or here comes carbon or whatever it is, right? That you're looking at. This is when it started to happen. Yes?
Well, there are certain patterns. So elements are not produced one at a time. They're produced in certain patterns.
Okay.
But you can look at their relative abundances.
Okay. I see.
And it is those things that change a lot over time.
I see. So it's not just here is when it appeared, but here's the percentage that it was during that time.
In some sense, I would say a more precise way of saying that would be perhaps that if you looked at something like chemical patterns in a star that is like the sun, so a relatively young star, a lot of different astrophysical events would have contributed to the chemical composition of the sun.
Okay.
And so they all get mixed together, and it's difficult to tell them apart. And so it all becomes one big mess. And so even though we can see, for example, that there's oxygen in the star, you can't trace it back to like individual type of process that produced it.
I see.
But as you look further and further back, those chemical patterns are becoming simpler and simpler. And in some cases, you can trace them to a specific event that just produced the chemical composition of that star.
I see. So it's multiple events that contributed to what happens to the particular star.
Yeah. So with any star that is relatively young like the sun, it would be lots and lots and lots of events.
What would an event be? Do we know kind of what some of those options are, or we just say something happened and we don't know exactly what it was?
So that would depend on the element. So different elements are produced in different abundances by different types of astrophysical processes. One of those events would be supernova explosions. Those are extremely violent processes. A lot of energy is available, so there's going to be a lot of nuclear reactions happening. There are other less violent processes. Certain stars at the ends of their lifetimes produce specific elements, and then those elements are ejected from the star and they're released into the medium around that star. And then later generations of stars form out of those events. Quite recently, not so long ago, only a few years back, we realized that sometimes mergers of stars contribute to the chemistry that we see. So there are special types of stars called neutron stars that are actually dead stars. But sometimes they can come together and they can merge, and that is an extremely violent process that can produce a lot of elements at the very far end of the periodic table. And we still don't fully understand where exactly those elements are coming from. So neutron star mergers are a proposed candidate mechanism. There could be others. and looking at abundances of those peculiar elements like europium, if you ever heard of that. If you like go all the way to the bottom of the periodic table, all of the elements with weird names. Yeah, so by looking at the abundances of those things in very old stars, we can pinpoint the mechanisms that contributed to their production.
So it could be something like two neutron stars just crashing into each other.
Yeah,
and those are quite massive, and because they're very, very dense, is my limited understanding of neutron stars. So you'd imagine there'd be so much energy as they crash into each other.
Yeah, so the way we believe that some of the heaviest elements form is through so-called neutron capture process. That's where you start with a lighter element, and then you throw a whole bunch of neutrons at it.
Right.
And as you keep doing that, that element grows, it gets bigger and bigger, and so it drifts further down the periodic table.
Yeah. It will get more protons, essentially.
And eventually some of those neutrons will convert into protons. Yeah,
and
that's
electrons.
right.
Okay.
So neutron-rich environments such as mergers of neutron stars would be an obvious candidate to look for the production of those really heavy elements.
That's super cool.
I know. I feel a bit giddy. Like, this is really cool to think about something like, elements. I was a biochemistry major a long time ago, so also kind of chemistry-minded. And you just kind of take for granted that these things exist, and with really no thought to how they got here and why we have them. And they're so essential for everything we have on Earth. But, they're just, stars are just out there crashing into each other, dying and all this. And that's how we got them.
And they're giving us all the cool elements that we need, like carbon and iron and even cobalt and molybdenum.
Yeah, we're all stardust.
That's wonderful.
Yeah, that is super cool. I do feel a little bit giddy now. But see, every time I talk to somebody, I'm a little bit less afraid of outer space.
Yeah, Mars mission.
Yeah, no thanks. So you get to use and look through a lot of telescopes, and you probably have over your career so far. I have a few of them that you have worked on or seen images from. The Subaru telescope in Hawaii. I did not know about that one. There's the James Webb telescope, obviously. Do you have a favorite telescope? If so, why? And kind of, everyone loves these images that come from telescopes. So can you just talk a little bit more about that process and what you like about it? And which one's your favorite?
Of course. I suppose the correct answer here would be that there is a specific scientific application for all of those world-class instruments. And so it would be difficult for me to choose a favorite because like the way you use those instruments
Okay,
is just
fair enough.
So different. So James Webb is in space, of course, which means that the atmosphere, the air in our atmosphere is not in the way.
Right.
And that means a couple of things. First of all, that means that you can look at infrared light that does not penetrate the atmosphere. So infrared light would be like light of color that is beyond red, that you cannot see with your eyes, but James Webb can see it.
Right.
And typically, this is very useful for observing colder objects.
Okay.
As if you ever heard like the phrase to glow red hot or to glow blue hot.
Yeah.
Right. So when you are hot, you are going to be glowing in visible light. But when you are cold, such as room temperature, you're still glowing, except you don't glow in visible light, right? Humans don't look like light bulbs. Yeah. But if you looked at humans with an infrared camera, you would see that they are actually glowing.
Right.
Yeah.
And that's the technology behind infrared camera and night vision.
Yeah,
Yes.
that's exactly right.
Okay.
At least some types of night vision.
Sometimes, the infrared types,
Yeah, so some of that infrared light does not penetrate the Earth's atmosphere. And so, at least in my research, it is useful to use James Webb to look at that infrared light.
Very nice.
It is also difficult to tell apart objects that are really close to each other in the sky if there's air in the way. Because if you ever looked at the night sky, the stars are twinkling.
Yes.
And that's because the light that is coming from those stars, it has to get through the atmosphere, and it's the air of the atmosphere that distorts it.
Yeah.
And so if you imagine there are two stars that are very close to each other, if you're looking at them through air, because of the distortion, you might not be able to tell them apart. But James Webb addresses that problem by being in space.
That's wonderful. Yeah.
The drawback, of course, is that it is very expensive to operate.
Yeah.
And so it is very good for looking at an individual object or a few objects that are close enough to each other to be in one or a small number of images. But if you want to do an all-sky survey, which is also part of my job as a galactic archaeologist, I need to look at a lot of old stars. Then a ground-based facility would be a more appropriate choice that you can use for an extended period of time, like multiple years, at a much lower cost, and just take a lot of observations of a very large area of the sky.
Wow. So, no favorite, difficult to pick, right? But each one has its purpose.
Yeah. Well, sorry, go ahead.
Oh, yeah. From a personal standpoint, you can't really visit James Webb, but you can go to Hawaii, and that can be a lot of fun.
Yeah.
So.
Yeah, that's true. I can imagine I'd pick Hawaii.
You pick Hawaii over the Mars. Over the Mars.
Yeah, I think something I feel like I have in common with astronomers and astrophysicists is that everybody loves a pretty picture. And I take a lot of my, microscopy images, which people are immediately drawn to, and they're easy to kind of capture people's attention because it's an image. And then obviously images of galaxies and stars and all these things, we kind of are a little bit lucky in that way, I think, to be able to show people things like that, as opposed to just, I don't know what chemists have. What do you guys have?
You just have like
just the
graphs and plots and the periodic table and symbols like HCO3 minus.
Yeah. So boring.
It's not boring. It's great.
But, astronomers are somewhat spoiled. It is much easier to give public talks when you've got lots of pretty pictures to show.
Yeah.
That might be not as easy to do in other fields.
For sure, because a picture is better than 1,000 words, as they say.
Yeah, that's true. Yeah, I had just recently seen a bunch of the images from when we had Michelle Thaler here at Notre Dame. She showed a lot of really beautiful images from the James Webb Telescope, and I hadn't seen a lot of them, and so now I have one on my fridge at home now that.
It was magical.
Yeah, she talked a lot about some of these similar things, and it is. I joke about being afraid of outer space, but it is kind of overwhelming to think about such emptiness, but then to remember that outer space made everything that it makes us who we are and allows us to exist. That is a kind of comforting thought in a sense. So I'm very excited to be talking.
No Mars,
but I kind of don't even know what question to ask next because I feel like you're going to have so many cool things to say.
I know.
So I don't know.
Well, I have a question.
Do you have a question you want to go?
So I want to just talk a little bit more about telescopes and the kind of information that you get from them. So you're getting images, and some of them we can see in the visible light, so it would be very similar to what we would see with our eyes. But there are also other things that we can't see with our eyes, but these telescopes have really nice detectors that can detect the light that we can't see, because we can only see a very, very small part of the entire light spectrum, or electromagnetic spectrum, right? The light spectrum. And that's where spectroscopy comes in, right? So I know astronomers do a lot of spectroscopy, looking at the light, different types of light. Can you explain a little bit to our lovely listeners what spectroscopy is? Very, very simple way, but also how you or astronomers in general use it to learn about the universe.
Of course. So one of the most common questions that I get is, how do you actually measure the chemical composition of a star?
Oh, yeah?
By just looking at it, right? You can't really go to that star and take a sample.
Yeah. So wait, you mean oxygen, when you look at it, doesn't say O2, and then carbon it's like a little C? It's not?
Well, it kind of does when you look at it through a spectrograph in some sense.
Okay. Very good, very good.
All right, so what we do is we take light from the star with a telescope, and then we decompose that light into the individual colors that light is made of. So, for example, every time you see a rainbow in the sky, the reason why that happens is because moisture drops in the atmosphere have done that for you. They have taken sunlight and they have decomposed it into all of the colors of the rainbow. And if you look at that rainbow very, very, very closely, you might be able to spot signatures of specific chemical elements.
Okay.
Right, so, for example, if you are considering hydrogen and you look at that rainbow, so the technical term for that is a spectrum.
Mm-hmm.
So it turns out that because of all of the atomic physics that is happening, that hydrogen atom is only able to absorb or emit a very specific set of very specific colors.
Okay.
So there is a very specific shade of red. We call it hydrogen alpha.
Yeah.
There is a very specific shade of blue. There is a couple of very specific shades of green. There are more of those colors in the infrared and in the ultraviolet, but they are very specific and they're very characteristic of hydrogen.
Okay.
And so if you look at a star and you see a pattern of all of those colors missing from the spectrum, then you begin to suspect that hydrogen is somehow involved.
And it's absorbing those colors away from the rest of the light that's
Yeah,
coming.
that's exactly right.
Wonderful.
Right. So the way atoms work is hydrogen is unable to touch all of the other shades.
Yeah, that's great. So you can go to a paint store and get these color swatches and match them to the colors and say, here's what hydrogen would look like, or the colors that it would take away. And then you could do this for helium. You could do this for something else.
Yeah. So the specific process, which I think is also quite exciting, how we actually do it, is we build computer simulations of stars.
Okay.
All right. So in a computer simulation, you can build your star, which is basically just a sphere of gas, and then you can work out how like pressure and all of the physics works out. In order to produce like this specific distribution of like density inside the star. And then you can quite literally shine virtual light out of that star using all of the physics that we know about how light is produced, which kind of brings us back to the point I made at the very beginning that you have to worry about microscopic atomic processes in astronomy because that's how that light is produced. And then the result of that simulation is it's going to tell you what the spectrum of that star is going to look like.
I see. So it tells you what you should expect if it has the characteristics that you defined.
That's exactly right.
Okay.
And then you can turn all of those knobs in your model so you can increase the abundance of some element, decrease the abundance of some element, and you can see how that spectrum changes. And so what you can do then is you can get a spectrum of a real star with a telescope, and you can compare them side by side, and then you just keep turning and twisting those knobs until you get the best match. And when you do, you know that like the positions of all of those knobs tell you something about the chemical composition of that star.
I see. So you say oxygen is this level, carbon is that level, or hydrogen this much, helium that much, because those are the knobs we set to get that spectrum that we're actually seeing.
Yeah, the technical term for that is model fitting.
Model fitting. Oh, yeah, if it fits the model that you put on. Okay, all right, model fitting.
That sounds quite like simple, but obviously I'm sure it's much more complicated what you do day to day to kind of make those things happen. So how much of your work is more I'm assuming a lot of it's computational because you can't set up a lab in outer space, but so basically you do a lot of this modeling then and then get information data, real data, and figure out how accurate your models are. That's kind of what I'm understanding.
Yeah, most of my work is calculating those models and comparing them to observed spectra. So I spend a lot of my day writing code. I get to use a lot of supercomputers, which is also kind of cool.
That's
awesome.
But also important to emphasize that astronomers have been doing this for a very long time. So you never do this from scratch. Like we have decades of experience, and there are software packages out there that can do a lot of that modeling. And so I'm just contributing one more layer on top of all of that.
I see.
Just tuning all of those instruments, getting them to work together, and getting them to work for the specific scientific application that I have.
So, I've talked to a lot of astronomers through various communities, at conferences and so on. And I say, what is one thing or, one of the main things that you should do if you want to become an astronomer? And almost everybody says, learn how to code, learn how to talk to a computer. And do you think there's value to that? I mean, it sounds like you do a lot of coding and a lot of at least reading code. Do you think this is a valuable thing?
Yeah, that is definitely very, very true.
Yeah.
I suppose this is a change that happened over the course of the last century or so. In the past, the amount of data that astronomers had to deal with was in general very small, because obtaining astronomical observations was a very difficult process, and most of it was done with things like human eyes.
Yeah.
And it's very difficult to quantify those observations, so it was more qualitative. But nowadays that we have imaging technology, and you don't just look at a star, but you can measure like its exact brightness, its exact position. You can get all of those numbers out. Astronomy has become a very data-driven science.
Right.
Right. So when you look at a spectrum of a star, it's just numbers. Right. You have all of those colors, and you have the intensity associated with each color, and it could be thousands, tens, hundreds of thousands of numbers, and you get those hundreds of thousands of numbers from every observation. And if you are working on a large survey that is going to look at 100,000 stars, then now all of a sudden, like, you have billions of those numbers. Wow. So you can't really do it with a calculator or a piece of paper.
Or a bunch of undergraduates.
Yeah, I don't think there are enough undergraduates in the world to do that. You have to teach a computer how to do your data analysis and then have the computer do it for you.
Right, because computers are really good at calculating things.
Yep, they're really good at doing simple calculations billions of times a second.
Wonderful.
Wow.
So all of you lovely listeners out there, if you want to become an astronomer, learn how to code.
I suppose that's probably true in a lot of fields.
In a lot of fields, yes. I think it's probably good advice for everybody.
Yeah,
But
I don't know a single thing about coding or computers, and I think probably the newest computer in my microbiology lab is like a Windows 2000 or something.
man, wow.
Because we don't need it to do very sophisticated things, really. We just need it to, like,
Take a picture.
take a picture.
Yeah, of a petri dish.
Yeah. So, or just,
Well,
yeah.
So we have a question that was submitted by one of our lovely listeners, and this actually relates to globular clusters. And maybe you can explain to us a little bit about what globular clusters are. But the question says, how do globular clusters form, and how do they stay together?
Well, the first one is definitely $1 million question. That's what we're all trying to figure out.
Hey, good question.
Some of the most mysterious objects in the galaxy, arguably, which is why they're so much fun to look at. So I guess we need to address what star clusters are to begin with.
Yeah.
All right, so if you look at the sun, then it travels through the galaxy on its own. There are no other stars in the same solar system as our sun.
Right, it's just dragging us along with it. Yeah, okay.
Yeah, there are certainly planets, comets,
right,
asteroids.
but no other stars
no other
really
stars.
in the vicinity. Yeah.
Yep, that's right. But we actually believe that the majority of stars form in families. So the way it happens is you start with a big cloud of gas, and then that cloud of gas collapses onto itself under its own weight. And then at some point during that collapse, it fragments into smaller subclouds, and then those subclouds become stars. And so typically you end up with a whole bunch of stars that all originated from the same cloud. And so they all have the same age because they formed at the same time. They have approximately the same chemical composition because they all originated from the same cloud. And that's what we would call a star cluster. And what happens next depends on how big the cluster is. So if your cluster is relatively small and only includes maybe a few hundred, a few thousand stars, then over time all of those stars are just going to disperse. There's not going to be anything holding them together.
Okay.
And in fact, this might be what happened to the sun. So it is on its own today, but perhaps 5 billion years ago when it formed, it had siblings.
But it was a small family.
It must have been a relatively small family because it ended up dispersing.
Okay.
There are lots of these small clusters that we see in the sky. They're called open clusters.
Yeah.
Open because they are dispersing over time. The most famous, perhaps, is Pleiades, which you can see with the naked eye.
Yeah.
If you find a sufficiently dark spot, just like with the naked eye, it looks like 7 stars very close to each other. With a telescope, you might be able to see a couple hundred.
Yeah. I've seen it with telescope, and it's really beautiful. You can see the fuzz of all the other stars, or a bunch of the other stars. But
And there's also
7,
some leftover gas inside the cluster, so that kind of provides some background glow. It's really nice in images.
Yeah.
And all of those open clusters are very young, typically. They're usually not older than maybe 100 million years, simply because they disperse over time. So older open clusters would not exist.
Okay.
But then if your family is much larger than that, if it includes hundreds of thousands of stars or perhaps over 1 million stars, which sometimes happens,
Yeah.
a very big family,
Yeah.
then because of the sheer number of stars and all of the mass in your cluster, it is going to be bound together by gravity.
Right.
And these clusters are able to survive for extended periods of time. So you might find these larger clusters to be quite old, perhaps as old as the universe itself. They do lose stars over time. Occasionally stars get knocked out. It's something that we call evaporation. But you start with such a large number of stars that even 10 billion years later, there's still a good number of stars remaining.
Wow.
And so these are the things that we call globular clusters.
Okay.
That's because they're roughly spherical in shape. So that's
Yeah.
just how like a large number of objects is going to arrange itself.
Yeah.
So they kind of look like globes. At least that's
Yeah, I
what
see.
astronomers who saw them in telescopes for the first time saw.
So big globs of stars.
Wow.
But what makes globular clusters interesting, there are approximately 150 of them in our galaxy. They exist in pretty much all galaxies, but the ones that are in our galaxy are easiest to look at because they're closest. What makes them special is that they have really strange chemical abundances that we are struggling to explain. Most globular clusters seem to have what we call multiple populations of stars with different chemical abundances.
Wow. So there's diversity within the population of stars that supposedly originated from the same thing, the same event. Is that
Yes.
correct? Yeah.
Yeah,
But
that is-
somehow they segregated into different groups.
That is very strange.
That is very strange. Now, can I ask a quick question on
Of
this?
course.
Are the groups that are similar to each other, are they closer to each other, or is the diversity kind of spread out?
So stars kind of move in a somewhat chaotic manner over time. And so when you let 10 billion years past, it would all be relatively well mixed.
Okay.
There are actually a lot of studies that look for subtle differences and
Yeah.
say the distribution of different populations across the cluster. And there are subtle differences that may or may not be statistically significant.
It's just above randomness.
Yeah, but
Yeah.
to first order, there is
They're
no
basically-
obvious segregation. They're mixed.
It's like you took them, put them in a pot, and just stirred the pot, and they're just all over the place. But there is diversity within their composition.
Yes, that's
Wow.
right. And those populations are often discrete, right? So you don't see like a continuous range of different oxygen abundances. There's just a bunch of stars with one abundance and a bunch of stars with another.
And they're just, I see. So there are big differences between them and not necessarily a gradient of differences. Is that what you're
Yes.
saying? Yeah.
Yeah,
Okay.
in fact, the differences are so big that they have noticeably different colors.
Wow.
Wow.
Yeah.
That's so cool. I'm sorry.
That is so
I'm
cool.
really,
Yeah.
I really am just kind of overwhelmed with how interesting this is. Because you don't really hear about stars being diverse. Like all these things that happening in outer space and what you guys study and all these different terms you had, I've always just like, there's stars and there's planets. But
Yeah.
to hear that there's just this wide range of diversity, which is similar to kind of how we talk about, you know, ecology and like these environmental diversities and factors that play a role in what the kinds of things we can observe. I never really thought of that occurring in outer space, something like stars.
Yeah, I didn't either. I think this is really
And my mind
quite
is just
enlightening.
kind of like,
Yeah, the
spinning.
gears are turning. So globular says, continue.
Okay, sorry,
This is
sorry.
Fantastic.
I'm derailing
Keep
everything.
going.
I'm so sorry.
We're just in awe.
I
So-
really am.
Yeah, and so because of like this difference as well as a number of other features that are quite strange and that we're struggling to explain about globular clusters, it is not entirely clear if they are simply normal star clusters like Pleiades but bigger,
Yeah.
or if they formed in some completely different way.
Okay.
And there are many hypotheses out there. Nothing is definitive so far. A lot of research is being done into it. But yeah, where globular clusters form and how they form is very much an open question.
Wow.
We believe that there might be two different types of globular clusters in our galaxy. There are those that probably formed inside our galaxy. And then there are a few that were stolen by our galaxy from outside. And you can tell them apart because like the way the chemical composition depends on the age of the cluster across these two populations is not quite the same.
Yeah.
But overall, it is an open question. We don't know exactly how globular clusters form, and we don't know how they get to this strange chemical state that we observe them in today.
Do we know how they stay together and not just explode far away from each other, or sometimes they do?
Well, they do lose stars over time through this
like
process
said,
called evaporation.
Yeah, okay.
But they are sufficiently big to hold themselves through their gravity. So all of those stars inside the cluster, they all attract each other.
They're tugging at each other as they rotate and move and spin and everything.
Yeah, just like the Earth is attracted to the sun.
Yeah.
Right.
Okay.
And even though some of the stars are lost, you start with such a large number of stars that they're still pretty big.
Yeah.
Some of the bigger globular clusters have well over 1 million stars, and they're so big and bright you can see them with the naked eye.
You know, I'm just trying to kind of imagine the scale of this. Again, this is not a scale that I'm used to. I work with proteins and enzymes that are, again, a very small scale. But considering that the sun is kind of an average-sized star, it's not really big, it's not really small, we can fit 1 million Earths inside it. And that's one star, and you're talking about 100 million stars. So I'm just trying to wrap my mind around that number. That's all, just the kind of the orders of magnitudes, and it's fascinating.
Yeah, I suppose it's important to establish a sense of scale, right? So 1 million stars sounds like a lot.
Yeah.
But for comparison, our galaxy, the Milky Way, is estimated to have 400 billion stars.
400 billion
my
with a
gosh.
B.
With a B.
Yeah, with a B. Okay.
Billion with a B. That should be the name of this episode.
Billion with a B.
Yeah, so a globular cluster is big in absolute terms, but compared to a galaxy like the Milky Way, it is a speck of dust.
This is just nothing. It's just a smear.
So it seems like there's just endless things then that astronomers can research. There's just seemingly literally endless new information that you can get because of things like the James Webb Telescope and their ability to continue to see further and further out, that there's just really no end to what
It's
could
the
be
universe.
Yeah, I guess, literally it is. That must be a hopeful thing as an astronomer, that like there's so much we don't know and you could always be discovering something new. I think other fields might not feel that same kind of sense of wonder and always something new coming in every day almost.
It is, certainly an optimistic perspective.
I can imagine that there's some other issues and things that go into that as well, but just it seems like you can just constantly be getting data all the time because there's so many telescopes and information and different ways to look at that information. To, look at one star and could probably have so much information just from one star that you can look at. Maybe I'm totally wrong about that, but
this is cool.
Yeah, that's absolutely right. So not only are we getting more and more data, and that is a process that is exploding exponentially, but also we find new ways of analyzing old data.
Right, because you have better computers and better models. Okay. Yeah, so this was a very good question from our lovely listener.
Do we know who?
He will remain anonymous.
Okay.
Chose to remain anonymous.
Okay.
Yeah.
Okay. That's fine.
A very good question.
Yeah.
All right.
So you also look at cold stars, which again is something I have not heard of before. So what are those? And probably another scale thing we can talk about is temperature, right? What is actually the scale of the temperatures we're talking about? Cold in outer space is going to be different than our idea of cold here on Earth, I'm sure.
Right.
Which is cold out today. So
the refrigerator.
So typically when we talk about temperatures of stars, we refer to the surface temperature.
Okay.
So that is a kind of temperature that you would get if you pointed an infrared thermometer, like the one you might use for cooking or whatnot. Stars tend to be much, much hotter on the inside. So the sun is something like 6,000 degrees Kelvin. So usually like a factor of 2 conversion to Fahrenheit or something.
Yeah.
But I'm gonna stick to Kelvin, which is basically the same thing as Celsius.
At
with a small
scale,
offset.
at that scale, pretty much the same.
Yeah.
In the interior of a star, temperatures could be much higher. They could be reaching millions of degrees. In fact, it has to be that hot in order for nuclear fusion to occur. But we can't see that. That's happening on the inside. So we can only infer that from models or indirectly. What we do see is the surface temperature. There is quite a range. There are stars that are very hot, possibly over 100,000 Kelvin compared to just like 6,000 of the sun. But there's also a lot of range going the other way. So in fact, the most common stars, sort of average star, if you just like looked at all of the stars in the galaxy, would be cooler than the sun. Not by a lot. It would be like somewhere between 3,000 and 4,000 Kelvin.
Okay.
And then if you go below that, at some point your star gets so cool that it is no longer able to run that nuclear fusion process. Because when you get cooler on the outside, you also get cooler on the inside. And once you like go below a certain threshold, sort of that nuclear fusion process stops. And you're still a star-like object, but you're no longer undergoing nuclear fusion. And so astronomers prefer to not even call these objects stars. They refer to them as brown dwarfs. And interestingly enough, brown has nothing to do with their actual color.
Okay.
It's just a conventional term.
Yeah, I don't know what brown is on the electromagnetic spectrum.
I don't know.
Yeah, so some of the coolest stars that you may be able to find might be 2,000 Kelvin.
Okay.
And then everything below that is going to be brown dwarfs.
Okay.
And some of those brown dwarfs could be quite literally room temperature.
Oh my goodness.
Wow. Okay.
So what astronomers refer to as a cool star would, I guess, vary from one researcher to another, but usually we sort of draw a cutoff around 3,000 degrees or so. So below 3,000 degrees, you start getting a mixture of stars and brown dwarfs. There are still stars that are just cool, and there are brown dwarfs that are hot by brown dwarf standards. And so that's where we draw the boundary. So anything that's sort of cooler than maybe 3,500 or 3,000 Kelvin is a cool star. So still much hotter than like this room.
Yeah.
Yes.
And why would you be interested in studying cold stars? What is unique about them that needs to be researched?
Yeah, that's a great question. There are a few things. One of the more interesting things is that they tend to be more sensitive to their chemical abundances. Right, so if you heat yourself up to a very high temperature, then eventually all of the molecules are going to fall apart into atoms. And then if you keep heating yourself even further, all of the atoms are going to fall apart into nuclei and electrons. And so your star becomes effectively just a soup of charged particles. And at that point, it is difficult to infer the chemical composition of your star just because everything is completely disorganized. And all of those specific signatures that you see in the spectrum that mostly come from those interactions between nuclei and electrons, they're all gone.
They're gone. That's it. There's
because you pretty much don't really have atoms anymore.
Right.
But then if you go the other way and you keep reducing the temperature, then first you get atoms. And so it gets a little bit easier to tell your chemical composition because you start seeing atomic features. And eventually you're going to start forming molecules in your atmosphere of the star, so in the outer layers.
Well, molecules. So you're actually combining atoms together to form molecules.
Yeah, which can only happen at low temperatures.
Yeah.
So that's why we're looking at cool stars. And those molecules have even more complicated spectral patterns, and so it's even easier to infer their presence.
Yeah.
And so if you change, say, the oxygen abundance in a very hot star, there might be very little change. If you change the oxygen abundance in, like, the sun, then some of the lines, some of the like missing gaps in the spectrum are going to be a little bit more prominent, but that would be a very subtle change. But if you look at a star that's like 2,000 degrees, then it's going to have water vapor in the atmosphere.
Awesome.
And water is a greenhouse gas, so it's going to be removing huge chunks of the spectrum.
Yes.
And changing that oxygen abundance even a little bit is just going to drastically change the way that spectrum looks.
Yeah.
And so it's much easier to measure that oxygen abundance if, like, a small turn in the knob results in a drastic change that's easy to observe.
So we're talking about molecules like water. What other molecules would we be looking at in these brown dwarfs or in these cold stars in general? Like, what are we looking at, like acetic acid or like something that complex, or are we talking about something like water or carbon dioxide? Would these actually occur?
Yeah, so that would depend very much on temperature.
Yeah.
Generally, the colder you go, the more complicated your molecules become.
How complex can we go?
So you start not that complex.
Yeah, can we make proteins and DNA and and have life? I don't know.
Perhaps not in quantities that are large enough to
Right.
detect spectroscopically, because you need a significant fraction of the atmosphere to be in the form of that molecule for you to be able to see it. But yeah, you start with water and titanium oxide. Those are some of the molecules that form at larger temperatures. And then as you go towards lower temperatures, methane, CH4, becomes very prominent.
Excellent.
And then at some of the lowest temperatures and some of the coolest brown dwarfs, you can look at more interesting things like ammonia, a few other things. Nothing super complicated.
Yeah.
You would not be like looking for signatures of complex organic compounds.
I mean, again, as a biochemist, this sounds like primordial soup here. There's water, methane, ammonia, and some of the very early experiments on how life emerged on Earth basically took a bunch of these molecules, mixed them together, and put a bunch of energy. And then we started seeing things like amino acids, the building blocks of proteins, living things, come together. I'm not saying that the stars have life, but it seems like it's all leading to the same thing, in a way, on stars or on a primordial soup on Earth, that these molecules just tend to form.
Well, yeah, I suppose the cooler your star is, the closer its environment would be to what you would consider a planet. So,
Okay, yeah, that would make sense.
Yeah.
yeah.
I didn't know any of that. That's
See, I'm making
super-
these connections, and
I
that's
know
really
you're
cool.
making the connection.
This is really cool.
This is why what happens when astronomer, biochemist, and microbiologist walk into a bar. This is the kind of conversation.
This is the kind of conversation.
Okay, so I could talk about astronomy and everything forever, but I do kind of want to know a little bit more about your journey both to astronomy and why you're here studying this, why you're here at Notre Dame studying this. Before we started recording, we just you were talking about where you grew up and where you've moved and all those kinds of things. So I don't know if you just kind of want to start talking about your journey in any way you want to, how you ended up where you are now, and tell us more. Because before we hit record, I was really intrigued, and then so I'm anxious to hear more.
Yeah, I suppose for most people, like, where are you from is like a simple one-word answer. My case is only a little bit more complicated than that. I've moved a couple of times in my life. I am actually Russian by birth. My parents moved to Cyprus at some point during my childhood, and I actually went to high school in Cyprus.
Wow.
I spent 3 years in London doing my undergraduate degree at University College London. Then I spent 5 years doing my PhD at UC San Diego.
Okay.
And I've been here at Notre Dame for a year and a half.
Okay.
And hopefully I will be here for the next year and a half.
We'll see.
My postdoc is 3 years.
Yeah.
Okay. All right. So yeah, you kind of have been all over the place. How do you find South Bend, the Rust Belt here? It's probably the most, well, probably people would say it's the most boring place out of all the places you've said you've lived, but I don't know. I like it here.
Well, I suppose it depends on whether you're used to it or not.
Yeah.
It might be boring to somebody else. It's quite a change compared to California.
Sure.
I missed the mountains a little bit,
Mm-hmm.
but I got to appreciate the Great Lakes quite a lot.
Yeah.
And the lush forests that you don't really get
Yeah.
in the desert.
Yeah.
I am quite an outdoorsy person. I'm trying to keep that up
Yeah.
out here in the Midwest.
Yeah.
Yeah.
I've been trying to engage as much as I can with local culture. My girlfriend took me to a corn maze last summer.
Wonderful.
That is very Midwestern.
You are, sir. You are incorporating right into the Rust Belt
Yes.
culture in
Yes.
the Midwest. Yes.
I'm born and raised here, so this is kind of all I know is Midwest. So I'm always interested to hear kind of what people who are transplants feel about this. And I think too, the Midwest, people are more familiar with science happening on the coasts, and the Midwest kind of gets ignored. But there's some really great science here, so that's why we're also excited to highlight science happening not just at Notre Dame, but everywhere here in the Midwest. So I'm glad you're getting accustomed to it. It's March 6th today.
Today, when we
And
record this,
it
yes.
snowed last night,
Yes.
It did.
and it's very cold, and
Yes.
it will be 60 degrees in a few days.
That's right.
So
If you don't like the weather, wait 20 minutes.
Just
Yeah.
wait, right?
Yeah,
Yeah.
just wait 20 minutes. It just changes. Yeah.
So how did you then end up in this field of astronomy? Is it something that you always were interested in? You know, there's obviously a lot of coding computer work as well, so you kind of almost have to have both interests, I would think, or the ability to do both of these things. But how'd you end up studying stars?
I started off as an amateur astronomer.
Okay.
So previously we mentioned that people who want to become astronomers should be looking at coding, and that is very fair, and that's probably also true in many other fields. But I would say a more important first step before you start learning how to code is to start looking at the sky.
Yeah. Yeah, for sure.
Yeah, that is a very important prerequisite.
Yeah.
At some point, my parents gave me a small telescope as a birthday gift.
Yeah.
And somehow I just got carried away.
Yeah.
And a lot of people tend to just look at some of the more obvious targets in the sky, and then over time they begin to believe that they're running out of things to look at. But the reality is that the sky is enormous, and if you like follow astronomy magazines and you look at like recent things happening in the sky, and if you try and look for more challenging targets, you kind of never really run out of things to do.
That is very true. That is very, very true. Yes. There's always something coming across our field of vision, and I've spent some time with my kids chasing celestial objects when they come through. Sometimes when it's very, very cold. It's always cold and dark.
Yes, it is the Midwest.
Well, the Midwest has just experienced two of the most extraordinary astronomical events in the universe.
Yeah. So I'm guessing one of them is the total eclipse
Correct,
that happened
yeah.
last year, which was fantastic. I was in Indianapolis for that.
We got really good weather against all odds.
Yes, it was fantastic. What's the second one?
The Northern Lights.
The Northern Lights.
Oh, that's right.
Yes.
I did not see it.
I did. It was awesome.
I
I did
did
a little
not-
bit here in South Bend. It's very hard
Yeah.
because of the light pollution, but you could barely see it, and it
Yeah.
actually showed up better on cameras. Like my phone camera was able to capture a little bit, and I don't know if it's just like AI exaggerating what it's looking at.
I think that's the experience that most people had.
Yeah.
Phone cameras happen to be sensitive to
Yeah.
the specific range of
Green,
colors
yeah,
that
exactly.
they need to be
Yeah.
sensitive to.
But it was fantastic.
What exactly are the Northern Lights? Sorry, I keep derailing
No,
with
this is
questions. I want to
perfect.
hear more about your
Yeah.
journey to hear. But what are the Northern Lights?
So those would be high energy particles coming from the sun. So the sun is constantly throwing things out into space around it. It's a very active star. A lot of things happening on the surface, and sometimes those things result to some material being ejected out.
Okay.
And when those particles hit our atmosphere, they transfer that energy to the atoms in our atmosphere.
Okay.
And then those elements, those atoms begin to glow.
So the energy turns into light, basically. Light energy. Okay. Cool.
Okay.
Cool.
Yeah, so
Very good.
typically the magnetic field of Earth is going to redirect most of those particles towards the poles. And so I always thought I would have to go to Alaska to see the
Yeah,
Northern
that's what
Lights.
I assumed. Yeah. Yeah.
But if you have a lot of those particles coming in at once, if there is a major event happening on the sun, then even with that redirection, there's still going to be a good chunk of them making it to much milder latitudes, such as those of the Midwest.
Wonderful.
So it must have been a fairly large event that happened then for us to be able to see.
It was a very rare event.
Yeah.
Wow.
That's
Wow.
great.
That's super cool.
And they're very difficult to predict also.
Yeah. That's because I remember seeing online, people are like, oh, the Northern Lights are here. I'm like, why didn't I hear about this? But yeah, I can imagine it is difficult to predict something that rare. So
You get a very short notice.
yeah. I still missed it even with that. So, okay, we can go back to your story now of how you started off as an amateur astronomer, you got your microscope, and then kind of how does one turn that into a scientific research career?
Yeah, I suppose if you spend a long enough time looking at the sky through a telescope and you like it, you kind of start considering it. Maybe I could get paid for doing that. So it seemed natural for me to get a degree in it. So I got a degree in astrophysics at University College London. And I enjoyed all of the quote-unquote lab work that was associated with that degree. Now, as astronomers, we don't have labs. So instead, we were getting some mini research experience in a sense. We had a teaching observatory with small telescopes, much larger than the one I had as a kid, much smaller than Subaru telescope in Hawaii, but good enough for students to get some data and do some analysis. And that seemed like a lot of fun. And so grad school seemed a natural next step. So I applied to a whole bunch of grad schools, and I got an offer from UC San Diego. So I spent 5 years there. And then it's just inertia.
Yeah.
I've been doing research for a living for 5 years.
Yeah.
Might as well keep on going.
Yeah. Yeah. So we're both postdocs here at Notre Dame, which is I haven't finished my first year as a postdoc yet. So you said you have a 3-year contract technically. So during your time as a postdoc, what are some of the questions that you're currently working on? I'm sure you touched on them as we had this conversation, but what are you doing specifically here at Notre Dame right now?
Yeah, so the main project that I'm currently working on has a very, I would say, unimaginative name. It's called the Prime Focus Spectrograph.
Okay, all right.
It is a very exciting project, but perhaps you wouldn't be able to infer that from the name itself.
So do we just always do that as scientists? We take something that's really exciting and give it the most boring name?
Well, I suppose in this case, that's definitely the case. Yeah. So PFS for short.
Yeah.
So what PFS is it's a new instrument. In fact, it's a new spectrograph that has been recently installed on the Subaru telescope in Hawaii. Subaru is one of the largest telescopes in the world. It's approximately 8 meters in diameter.
Wow.
The biggest telescope in the world is only slightly larger than 10. So it is pretty high up there. It sits on top of Mauna Kea, which is the highest peak in Hawaii on the Big Island. It's really high up, so you reduce the amount of air as much as you can. It's not quite in space, but it is better than it would have been had it been at sea level instead of the summit of Mauna Kea, which is like 14,000 feet.
Wow.
And what that new instrument can do, PFS, that can take spectra of a very large number of stars at the same time.
Yeah.
In fact, we can take approximately 2,500 spectra all at once.
Wow.
Right, so what that instrument can do is got lots of optic fibers. Those are like cables that can transfer light, and a whole bunch of small robotic arms that can place those fibers exactly where you want them to go. And there are over 2,000 of those fibers, and you can just point the telescope at the sky, and you can place those fibers in individual stars. And then all of that light travels down those fibers into the spectroscope that then gives us the spectra of all of those stars. And that is very good for large surveys. Let's say if you're trying to understand the chemical history of our galaxy, you're going to have to look at a very large number of stars. And so that is the plan. So over the next few years, we will be observing old stars. So we'll be taking their spectra. We will be getting an enormous amount of data. Because every time you point the telescope at something, you just get 2,500 spectra.
Wow. Wow. That's a scientist's dream to have like that much data. To
And
analyze.
also a nightmare to analyze all of
Yeah.
that. Yeah.
Well, I can imagine.
Well, that's where computers come in.
Yeah.
Yeah, so in fact, my job is developing all of the software and all of the code that will be working behind the scenes that will take all of that data from the telescope and turn it into chemical abundances.
Wow. So that's very clever to use these fibers to actually focus on the stars, the individual stars. Super cool. So then the $1 million question is, how often do you get to go to Hawaii, and can you take us with you? I'll learn the code.
The answer to that is unfortunately quite disappointing. So in the past, and not so distant past, maybe a couple decades ago, in order to observe, you had to go to the site of the telescope.
Yeah.
That is mostly not the case anymore.
So they ruined it, is what you're saying.
Technology ruined that aspect of astronomy, as nowadays you can do virtually everything remotely.
Yeah.
I got to go to Hawaii once as a grad student, and that was not really because I desperately needed to, but because my PhD advisor had a policy that everybody who works with telescopes in Hawaii gets to go to Hawaii to observe in person at least once.
I'm sure
right.
it's very helpful to actually do that. Joking aside, like it is very helpful to just see it in person and to appreciate it.
Oh, for sure. It's also easier to communicate with observatory staff when things go
Well,
wrong.
Because
But typically, it is considered not worth the cost of travel, unfortunately, nowadays. So you don't get to do that often.
Yeah, so we're not going to Hawaii.
Not going to Hawaii. Okay, that's fine.
Yeah, so the real answer is that if you would like to actually go to all of those amazing sites on a regular basis, then you have to be involved in the hardware. Right? So if you're one of the folks who are developing those instruments and actually like screwing bolts in and like putting cables together, then you would be spending a lot of time in Hawaii.
The engineering side and the hardware side of things.
Yeah, there's a whole huge chunk of astronomy that we call instrumentation. That's where people build those things that eventually get installed on telescopes. But I'm not that. I do mostly theoretical research, modeling. I do analysis of data. So I don't get to go to Hawaii all that often.
Wow. I just want to leave us with this one question. If there was one thing, or maybe a couple of things, that you would hope people to know about astronomy or astrophysics, and you want to leave our lovely listeners with, what would that one or couple of things be?
Yeah, that is an interesting question to think about. I suppose just building on something that I mentioned earlier, I want to emphasize that astronomy is likely the most accessible and inclusive science of all of them, because in order to be an astronomer at one level or another, the only thing you need is the sky above you, and that is not going away. It doesn't matter if you're rich or poor. It doesn't matter where you are in the world. The sky will always be there, and in order to see it, all you need to do is look up and, well, sometimes wait for good weather.
Yes.
Maybe you might want to get away from city lights.
Yeah.
We actually have a protected dark sky park only about 40 minutes out of South Bend.
Yeah, not too far away from here. Yeah, it's just
The
north of here.
Dr. Lawless, I think, is what it's called. So, yeah, anybody can get involved. Astronomy is not just about all of the discoveries that you hear about on the news or on the internet or through this podcast. It's also about just looking at the sky. It is very cheap. Everybody can do it. And there is an infinite number of things to discover. You can just keep doing that for as long as you want. And you're never going to run out of exciting things to see.
That's wonderful.
Yeah, it almost makes me a bit emotional. It's really a beautiful thing to leave people with, and to remember that all you have to do is look up and there's a whole world,
The whole universe.
a whole universe that is waiting to be explored. And you don't have to, there's lots of ways. You don't have to be a coder. You can do all kinds of ways, things to
Just look up.
just look up.
Just look up.
So,
Well, Roman, this has been inspiring, and
this has been incredible.
it's been awesome because we are now thinking about scales that we have not thought about in a long time. So thank you so much for being on the podcast.
Of course, it was my pleasure.
Thank you. And thank you to our lovely listeners.
Yes, thank you, everyone.
At the end of our show, we would like to thank you, our lovely listeners, and our awesome audience for spending your time with us. We thank the Notre Dame College of Science and the Indiana University South Bend College of Arts and Sciences. Special thanks to the wonderful people at the Notre Dame Studios. Coming to you from beautiful South Bend, Indiana, in the heart of the Rust Belt, this is Rust Belt Science. I'm Shahir Rizk.
And I'm Maggie Fink.
And we'll catch you next time.